So, dear students, welcome to day 17 of digital hardware design using VHDL course for 40 hours. If you remember yesterday, we have discussed about the finite state machines, and I have taken the example of a simple traffic light controller. Could you please mute everybody? Okay. So, yesterday we were discussing about the finite state machines, where I have taken an example of a simple traffic light controller in which you have seen I have implemented a traffic light controller first of all with the help of Moore machine, where in which the output is only the function of the state of the flip-flops, where whereas when I have implemented it with the Mealy machine by introducing a sensor as an input, in which the output depends upon the input as well as the states of the machine. Okay, in both the cases we have seen we have implemented this FSN using the conventional uh, paper pen approach, which we have been teach in the classes in digital electronic course, and also I have uh, I have discussed it by designing it with using VSDL and show you the simulation and verification results, and we have successfully verified that also. So that was a very important topic. What I suggest that you people may please uh, keep practicing some other types of FSM designs which are in real time, which can be implemented in real time scenarios like your vending machine, sequence detectors, door locks. All these can be implemented with the help of FSMs. Right now, almost if you see that we have completed and touched upon uh, basic concepts of VHDL programming. Right. Uh, Now there are still some more advanced concepts are there which I would like to uh, discuss with you so that you can use them as per your requirement and as per your applications. However, uh, some of these concepts hardly requires because most of the things we can do with the normal modeling approaches. Okay, so out of these three advanced concepts which I have written over here, first is generic, with select, and when else. Apart from that, there are some other concepts also. But out of these three, if I will say generic is most important and it is somewhat different basically. Uh, right. So we will start with from this and see the importance and also discuss what we can do with this, right? And how it can be useful in building complex systems. Okay. So what is basically a generic or generic statement in VHDL basically? So if we say a generic statement in VHDL allow a designer to create parameterized hardware module, okay, whose characteristics such as width, depth, or timing can be configured at instantaneous time. What happens with this? This improves design flexibility, portability, and code reuse, making generic an essential feature for developing scalable FPGA and ASIC designs. Scalable, basically. This is the important thing. So, what is there basically? See, till now, when we say that we want to design comparator, we want to design ALU, okay, yeah, we want to design adder, or yeah, we want to design counter, then in that particular case, in every case, we fix the, you can say, number. Means we want to design a 4-bit adder, or we want to design an 8-bit adder, or we want to design a 16-bit adder. Okay, so in that case, when we design, we fix the number of bits in every case till now what we have designed. Okay, but what we can do with the help of generic statement, we can create scalable means scalable IPs, you can say scalable intellectual property codes. Okay, where what you can do just when we are using standard IPs. So in that these standard IPs are configurable. Configurable means we can configure their inputs. Okay, up to a certain range. If you remember, we have when we have discussed standard IPs, and I have taken the example of adder subtractor in which I have used adder subtractor. So that adder subtractor is configurable in the sense that the range of inputs is varying from 1 to 256. Okay, and you can customize that particular IP as per your requirement for 4 bit, for 5 bit, 6 bit, for 8 bit, for 10 bits, as per your requirement. So this is where the generic comes into picture. How is it possible? How can you make them customizable? It is only and only when you use this generic statement. You can make customizable IPs, or you can create customizable structural style of modeling designs. I hope you got my point, what I'm trying to say to you. Okay, we'll take one example and then understand what I am trying to say to you. Okay, and how it can be introduced for that. Actually, it is introduced inside the entity where you are defining the entity name, and after that you need to define generic name. Okay, like this, generic followed by generic name, whatever you want to create, data type and default type. Okay, similarly, any other means the number of things you want to parameterized or customized. One input is there, two input is there, three input is there, what you want. And after that, we'll do the normal port declaration and end the entity. So it is defined inside the entity only. Okay, so let us take an example so that you can understand what I am referring to. If you remember, just few classes back, we have designed a mode n counter where I have taken that n as 10. Okay, I have fixed that number. Okay, but what if I would like to design a I want to design an IP of mode n type of counter where I can fix n maximum value as 16 or 24, whatever I want. Okay, and whenever I want, I am customize it for lower values. Okay, just like for mode 5, mode 6, mode 7, mode 8, mode 9. Means once I design but customize it for different values of the mode counter. Okay, so that we can do, and let's see how it can be done. Okay, so in mode counter, if you remember, we need to we need to restrict the count. Okay, if this is a mode n counter I'm going to design, so I have to count it from 0 to n minus 1, right? Suppose I'm taking n as 10, so I need to count it from 0 to n minus 1, that is 9. If I will be designing is as mode 16, I need to count it from 0 to 15. Similarly, so what I did in this program, you can see over here, I am designing a mode n counter. Simply, I have introduced the necessary libraries over here till now. After that, I have written entity mode n is, and now you can see this is the new thing. Okay, I have written generic. I have defined and fixed the value of n colon integer type colon equal to 16. Okay, colon equal to 16. Right? So it will count from the maximum value of the counter I have fixed, that is 16. You may choose any value of this. You may go up to 24 or 40, 50, whatever you want. Okay. So the range of the counter increases. This is the maximum value that you have to define. Later on, when you will fix it and make this IP, and after that if you want to use it, then you can use it as a 5-bit count, as a mode 5 counter, mode 8 counter, mode 10 counter, mode 15 counter, maximum range you can go up to. Now if I will be using it as a mode 16 counter, I need output in at least 4 bits. So because the count will go from 00000 to 1111 maximum. Okay, so I need 4 bits to represent. So I have also created another generic variable width, integer type. Okay, and number I have specified 4. Right? So this is the and put colon. So this is basically the generic statement I have created. After that, simply port, clock, reset in std underscore logic, y out std underscore logic underscore vector. Now you can see the output range should be 0 to 3. So what I have done, 0 to width minus 1. So that 4 minus 1 would become 3. So we are making generalized program. After that, architecture mode and arc of mode n is signal. Okay, we want an intermediate signal to store the intermediate states. That should also be of 0 to 3. That is 0 to width minus 1. Process clock reset begin. If reset equal to 1, initially that u should be 000. Else if clock equal to 1 and clock tick event, then if your value of this variable is not equal to 15, that is n minus 1, then it keeps on counting. Otherwise, it will again go back to 0. Rest you can see else if, else null, and if, and process. This type of counter we have already designed, but I have just modified it by using generic keyword. Okay, over here, and do the necessary changes at these places. Okay, these are the necessary changes that you need. I have done in it. Okay, now why I have made it generalized, because when you will customize this IP and you will try to use, then you will find out that we can customize this counter for various type of counts. This is the basically the idea behind this. These changes we have done, right, in the program at these places. Rest of the things are same. Now, if you want, you can check and implement this using the software also. That how it can be customizable, how it is can be used and customized. Okay, let's see. It is taking some time. Let's create a project. Let's give its name as mode encounter. Okay, let's write this mode n. Next, create file. It should be similar to the name of the entity, right? Should be similar to the name of the. Let's say this is mode n. Second entity was mode n. Let me copy this. Okay. Or please mute yourself. Unmute yourself. Please mute yourself. Okay. So we have given the name mode n. Followed by the architecture name. Just put the name of the architecture over here. Okay. We'll copy the code from there, what we have written. Okay, now you can see in this way it can be defined, right? In this way it can be defined. You can save it. There should not there it seems that there should not be there is no any error, and we can run simulation to check it out. Okay, to test that design, we just follow the same process that we followed previously. Force constant, make reset 1, then clock, post constant 0 and try to run for a specified time. Okay, now you can see initially the output is 0. This n and if it's you have been shown as a constant values. So initially the output is gets resetted. Okay, now as we'll apply clock and make reset 0, you can see post constant 0 and try to apply clock over here. Force clock. Okay, here leading edge value would be leading edge would be 1 and trailing edge value would be 0. Okay, now run for a specified time. You can see now in this closely it is simply counts from 0 to 15. Okay, you can check. As you will apply the clock, it starts counting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 because it is showing the results in hexadecimal, and after that automatically it will become 0, 1, 2, 3, 4, 5, 6, 7 and so on and so on. It will follow till then the clock has been there. It keeps on counting. Okay, till the clock is there and it starts counting from 0 only. Okay, if you want you can change the radix. Okay, you can change the radix to simple uh, unsigned decimal. Okay, you can change the radix to unsigned decimal. So it will show you like this: 0, 1, 2, 3, 4, 5 up to 15 and then again back from start from 0. So we have successfully checked that this particular code is perfectly working, but how we can customize it for different types of configurations? That is the main use of generic keyword. So that we will see. Now what we can do, because we have successfully verified this program, it is perfectly working. What we can do, we can package this IP. We can make IP of it, just like we did in previous cases. So let me show you. Create and package new IP definition. है ना? Package your current project. Yes, it will be saved inside the Vivado repository. Okay, so let me create a new folder. Let's say name is mode 10 count. Mode n count. I have created a folder with the name mode n count inside the repository only. Select. So your all design will be saved inside this folder now. Next. Okay. Finish. Let me package this. Okay. Now you can see over here identification compatibility. Okay. So that is fine. There is no change in it. File groups that we want to include. Okay. Then ports customize parameter. This is a new thing you can see. We have include two customized parameters. Previously, this was not shown when we were packaging the IP. So this there is uh, nothing has been shown inside it. Okay, you may check that. Okay, previously when you have packaged, there is nothing like that. Okay, but over here we have make it customizable. After that, ports and interfaces. We have clocks, reset, and output Y. Simple. Output Y, right? Of this type. Then customize GUI. You can see over here. It will show you like this and show you can customize this and width accordingly. Okay, and width accordingly. You can customize this like this. Okay, review and package. Okay, so it is created with this name and saved inside this repository. Let me repackage it. Okay, now my IP definition has been created. I have created an IP of the project. Okay, now if I want to use it, I can use it. How I will use it? I can use this IP of counter in any of my project wherever I require. So yesterday you have seen that I have created a traffic light controller. If I want to use that IP inside a traffic light controller, I can use that IP as a counter IP and customize it for my required number of count as I want. Okay, I can do that also. Let me show you how can we customize and how it is available. So let's try to create a new design now, new project. है ना? Mod and IP. Give count IP, or you can say counter IP. Simple. Counter IP. Next, next. Actually, you want to create a design file. So next, next. Finish. Yes. Okay. I have not included anything inside it. Presently, you can see I have not created any file. Nothing. I've just created a project with the name counter IP. Now I will go for the create block design. You can see over here. I will go for the create block design. Okay, the design name you can choose anything. Okay, let me create the name. I want to create a counter, or I want to create a mod mod 10 counter. Okay, mod 10. So I have just given the name mod 10. Okay, now just click on over here and search for your IP mod n. Now it is there. You can choose it, right? It is there on it itself. Now by default it is of mod 16, but in your program, if you want, Less than that, you can customize it. How we can customize it? You can check it out. Okay, there is an option. What we can do? We can put 10 over here. Okay, and for 10, there are still 4 bits required. But if I will be using or customize it for 8 mod 8 count, then in that case I will be using it for 3 bits only. So I need to change the n value and bits value in connection together. Okay, this is our requirement and our even means it is the uh, uh, responsibility of the user to change the values of n and bits responsibly. Okay, or otherwise you will not get the correct answer. Okay, so suppose I want to just design it for mode 10. So accordingly, I need to change the width 4 because to represent mode 10 count still I need 4 bits. Okay, so automatically you can see the things has been changed from to here. Okay, you can see things are changing here as you will changing the width. Okay, now we have customized this counter for only for we have customized this counter only for 10 count, mode 10 count. Now it will count from 0 to 10 only, not more than that. 0 to 9 only, sorry, not more than that. For that, what you need to do, let me create the ports first of all. Okay, so these are the ports created when I does the connection. Now, if you want to check whether it is acting like a mode 10 counter or not, you need to you need to go into the design source. Okay, and create HDL wrapper. You need to create the HDL wrapper. Okay, means now it will automatically create a HDL wrapper for you for which you can simulate it. You can see an HDL wrapper is created for you over here where it is including this design, mode design. Okay, and if you want to check it out, this HDL wrapper, how it looks like, you can check it out. You can see over here now, it has created a code for you which can be synthesized. Automatically it has taken 0 to 3 and it automatically it will take the count mode 10 as per our generic definitions. Okay, if you want you can run this. Let me show to you. Okay, now let's see. So what we will do, let's see, same thing that we have performed for previous simulation. Reset force constant, put it 0, because it is active low. In our IP, it is shown as active low. Okay, and clock clock is positive as triggered. So clock would be same. Initially, let's make it 0 and run it for a specified period of time. Now you can see over here, okay, there is some problem. The output is not updated. Let me reshare, restart it. Okay, uh, I think we have to apply force constant to 1. Let make clock initially 0 and let me run now. Okay, we have to apply 1 to the reset, not 0. Okay, that's why there was a problem, right? Now you can see after that, make reset disabled and let apply the clock over here, where the leading edge value would be 1 and trailing edge value would be 0. Okay, and run for a specified period of time. Now check it out whether it is work, whether it will go to 0 to 9 or more than that. Okay, that we have to check it out. So make it zoom. Yeah, you can see over here closely. This counter we have customized. Now it is acting as a mode 10 count. However, with the help of generic, we have made it for maximum 16 count from 0 to 15. But when I customize it and use it in a design for only 10 counts, it is counting from 0 to 9 only. And after that, again, it is counting from 0 to 9, 0 to 9, 0 to 9, 0 to 9. So this is the achievement that we have done with the help of generic keyword. We can make scalable designs. We can make scalable ICs. It is not now that if I want three counters in my project of different value, I need to write the code from the scratch for all these three counters. Rather, what I would do, I will design a single counter of maximum value and use the generic keyword. And in main design, I will reuse them as per my requirement and customize them for specific counts. So this is the power of generic keyword, okay, which will help you in designing complex systems. Okay, I hope you have understood this concept. If all of you have understood this concept, please uh, say yes in chat box. Or if you have any doubt, please let me know. This we have completed the use of generic keyword actually. Okay, the use of generic keyword we have checked. Tell me students, if you have any doubt, please let me know. Or all clear, or nobody is listening. Anybody from you? Have you understood? Nobody is responding. Okay, then let's start with a new topic, another topic with select statement in VHDL. With select statement in VHDL. Okay, just wait for 2 seconds. Okay, okay, dear students. Uh, Now let us discuss a new topic with select statement. What is a with select statement in VHDL and how we can use this statement? Okay, you can see over here the bit select statement in VHDL. It is a concurrent signal assignment statement. Okay, which is used to implement multiplexer, decoders, and combination logic in one go. In one line, you can implement these type of circuits at a very fast pace. Okay. For an example, let us understand with this is the syntax with followed by the select signal. Select, you have to write these are the keywords, both are the keywords, these both are the keywords, okay, and output value 1 when choice 1, value 2 when choice 2, value 3, and so on to like that. Comma, 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 and final colon. So this is a single statement, okay. This is a single statement where output is being verified. So uh, this type of statements help in implementing these basic circuit elements in a single line so that we can have some fast so that we can have some fast implementations. Okay, so how it can be done? Let's see. Library IEEE and use IEEE. These are the libraries that we have included. After that, Mux 441. I am implementing the concept or showing you the concept with the help of a designing of a 4:1 Mux. Okay, so you can see I have defined four inputs because 4 into 1 Mux is having four inputs, two select lines. So I have created a select variable of 2-bit output std underscore logic type. Then architecture begin. Now you can see over here I'm using with cell on which I want to select. This is a selection signal. Select with select. Okay, these are the keywords, right? These are the keywords with and select. These are the keywords. Similarly, is also a keyword over here. So what we are saying, y, which is the final output, gets the value of a when select signal is 0, 0, comma b when select signal is 0, 1, c when select signal is 1, 0, d when select signal is 1, 1. And apart from that, if any value comes, we have created it, or you can specify it as high impedance state also when others. And now I have put the semicolon. So this is from here to here. This is a single statement which in which we can uh, updating the output. It has been possible with the help of only with select statement. Okay, so this is the idea behind this, and if you want, you can implement this type of 4:1 mux or circuits, or try it by yourself. You can try decoders, or you can try demultiplexer. Okay, right? So this is the use case of with select. Okay, statement with select statement in VHDL. Let me check with select statement. Right now, similar to with select, we have another statement that is called when else statement. Okay, which is very much similar to with select also, because when else statement is also a concurrent conditional assignment statement. It assigns a value signal based on one or more conditions. The conditions are evaluated from left to right, and the first true condition determines the output, giving its priority. Okay, same example. Okay, you can try to implement. Okay, on the software that is 4:1 mix design using now when else. Rest of the things are same as the previous example. Only what changes are there with select. Same thing is there. We have to use with select. With cell select. No, with select should not be used. As per syntax, this should be removed. Okay, yeah. Only we have to use like this. Y final output gets the value of A when select signal is 0, 0, else when else B when select signal is 0, 1, else C when select signal is 0, 1, 0, and else if all these three conditions are false, the output should be D. And you can see previously if we want to implement a 4:1 multiplexer, so either we were going to the we were using the if statement or case statement using the procedural uh, and go for the sequential execution, because by using process we are uh, making the design making our design execution as sequential in nature. But with the help of this with select and when else statement, we can implement these type of conditional designs, okay, with the help of and make them to execute concurrently, right, in a single line. And this approach is very much useful because it saves somewhere somehow of our hardware also at the synthesize time. Okay, so this is the use case of when else statement. Okay, right. So these are some of the topics that I would like to discuss with you. Okay, I want to like discuss with you initially, right? Some advanced topics in some more advanced concepts in BHD. Okay, now apart from this, so this is completed. Some more advanced concept in BSDN. If you find any new concept or you find any difficulty in any new concept, you please write to me. Okay, I will prepare a video for you or use case for you so that you can understand. If you find any difficulty in any other concept, okay, because covering all concepts uh, at this level of your understanding, it would be difficult for you because but when you will learn more, you can able to find the applications, the right use case, so as to use the right advanced concept. Okay, now we can uh, discuss some new topics now or shift our topic to day 18. Okay, let's see. Some of the part of day 18 I will cover today itself. Okay, because this is very important also. So let's cover some of the part of it today only. Okay, FPGA, Field Programmable Gate Array. We are talking about this lots of time. Hmm? Tuning the whenever we are testing any program, you have seen that I have to choose one FPGA board. Okay, so let us discuss something about the FPGA internal architecture. What is there inside it, and how can we? What are the things that can be configured inside it? Okay, and what is the process of configuration? Let's discuss on it. Right. So you can see over here, field FPGA is field programmable gate array. So this the block you can see over here. It is the FPGA chip. Okay, shown to you, and this FPGA chip inside just at the interface you will find that there are some green color blocks. These blocks are called as input output blocks through which you can basically basically communicate with the FPGA, or you can say input output pins, right? Apart from that, inside this FPGA you can find there are some blue color blocks. These blue color blocks are the main building blocks where actually your program or design is going to reside. These are termed as CLBs, configurable logic blocks. Actually, these are the blocks which are being configured as per your program and change their nature. Okay, these are termed as CLBs, configurable logic blocks. Apart from that, configurable logic, although configurable logic blocks are abundant in nature inside the FPGA. Okay, there is a good number of CLBs, and these can be utilized in the program by the program most of the times. But there are some special hardware dedicated blocks also available where you can initiate them in your design just like the standard IPs and use them for your work. Just like it is having internal block RAMs available. Various block RAMs are available. We have seen that we have designed our own RAM, but that RAM is actually utilizing the CLBs. But if we want a standard RAM or a standard memory area, so we can use that memory area also by initiating the VRAM in our design, because VRAM is available in the form of standard IP, okay, and we can directly use it in our design. Similar to VRAM, there are multipliers and other important hardware circuitry is available which you can initiate in your design and customize it as per your requirement and use it for your application. Okay, so this is the small introduction about the internal architecture of FPGA. Okay, FPGA families basically. So there is a long list of FPGAs nowadays. Initially, FPGAs were fabricated or designed with the by Xilinx company. Later on, this company has been acquired by AMD, Advanced Micron Devices nowadays, and we will be seeing that now AMD and new FPGAs are only being used or available inside its new standard software. Okay, these were the list of some old software or old FPGAs which were there. Some of them are still exist inside the library and are being used, but some of them are obsolete. Okay, just if I will talk about this Spartan family, this has been obsoleted. Previously, the Spartan FPGAs are family FPGAs are very much in use and has been taught from, you can say, from the era of 2000 to 2015 or so. Later on, after 2015, Vertex family has taken over and we have the Vertex family FPGAs. After that, nowadays SOCs are there, high-end SOCs are there, which are being utilized. Okay, and we are learning them. Okay, all these FPGAs are being developed on a specific technology node. Technology node, you can understand. I told you in the first class that everything is made up of inside the FPGA is made up of transistor basically. So the transistor size, gate sizes is technology node. Means the transistor which we are going to use inside our FPGA, basically on which technology node this FPGA has been made up of. So 40 nanometer, 65 nanometer technology nodes are there. Nodes FPGAs are there. If we talk about a simple CLB, just like this block over here, if I want to deep dive inside this CLB more, so what should be there? You can see these CLBs are available like this and they are connected in this fashion to each other. One CLB to another CLB, one CLB to another CLB, and they are connected. Some matrix wires are routed all along around them so that any CLB can be connected to any CLB. Okay, this small gray box you can see, this is termed as switching matrix, where we where the CLB's wires are configured and connected to another CLB wires. Okay, so this is a very uh, just like your electrical wires are routed, and in between you can put some switch or connector, so that you can connect one set of wires to another set of wires, so that you can route the data to another house. So it is the same thing over here itself. Okay, if we deep dive inside this CLB part, you can see over here this CLB is further contained four slices: slice 1, slice 2, slice 3, slice 4. Four slices basically. Okay, and inside every slice there are two logic cells. Inside every slice there are two logic cells. Further, if I want to check what inside the logic cell. So inside this logic cell, you can see there are LUTs, lookup tables, what we can say. Four input lookup tables are there. Previously, the old FPGAs or old legacy families are built upon four input lookup tables. Nowadays, the latest FPGAs, they are using six input lookup tables. Okay, but inside this logic cell, we have a lookup table. This lookup table is having a dynamic nature. It can be configured as a simple lookup table for implementing normal designs. It can convert its nature to RAM, or it can also convert its nature to shift register. Depending upon the requirement, we can this LUT changes its nature as per the design perspective. Apart from that, there are some multiplexers and registers are there in order to store the data and route the data. So inside the slice we have logic cells, and inside the logic cells we have these things. Okay, so I thought you have understood. So a CLB contain four slices, and a slice contain two logic cells. And inside the logic cells we have LUTs, MUX, and registers. These are the actually resources inside a CLB, okay, which are being configured by the logic in order to implement it. Okay, fine. Apart from that, I have told you that there are some RAM blocks available, multipliers available. So this diagram is shown to you where you have find this. So this square is CLBs. There are some dedicated multipliers, and there are some dedicated RAM blocks also. Okay, we can use these as per our requirement of the design because they are hardware dedicated blocks, but they are available in the form of standard IPs. We can initiate them and then utilize them in our program directly. Inside the FPG also, there is a clock tree, a simple clock tree, because there are lots of CLBs inside CLB slices, slices inside logic cells. Inside the logic cells, we have lots of registers. Okay, so all of them require clock, and so there is a proper arrangement of clock or distribution of clock inside the FPG architecture properly in a particular fashion. Okay, so that there should not be any clock delay and clock skew occurs from traveling of clock signal from one point to another. All of them, all registers which are involved in the designing, they can be triggered at the same instance of time. So there is a proper routing of clock inside the FPGA, which is sometimes referred as a clock tree. Also, we'll discuss more about it later on. Clock tree, okay, and this clock tree is being designed in such a manner so that minimum power consumption takes place as well as minimum clock skew takes place. Okay. How can we generate this clock signal? There is a digital clock manager. The clock is coming from the outside world, or the onboard oscillator is generating the clock. Further, there is a clock manager inside the FPGA which can generate various daughter clocks to internal clock trees or to the output pin as per your configuration or as per your requirement. Okay, so this is about the FPGA internal architecture. Okay, this is about the FPGA internal architecture. And there are some of the things at a broad level, some of the things available inside the FPGA. Okay, if we talk about Zinc FPGA, if I would talk about the Zinc FPGA, then you can see, let me talk about Zinc FPGA specifically, Z by NQ FPGA, which we are following. Internal architecture. So this is a 6-input FPGA. You can see like this. This is standard. This is the standard Zinc FPGA. You can see. Uh, Let me choose another. Okay, this would be fine. Okay, okay, right. Inside it, you can see we are actually using this type of family FPGA, Zinc FPGA family. So Zinc is basically a SSOC, system on chip. Okay, you can see system on chip versus FPGA, SOC FPGA versus SOC. What is the difference? One of the main difference between FPGA, SOC, and SOC is in general is when whether there is an FPGA or not. Examples of SOCs are generally used in single board computers such as Raspberries, gadgets such as smartphones and tablets. Okay, so in Zinc SOC, what is there? There is two parts. One is called processing system and another is called logic. So the FPGA chip is divided into two parts basically. One is called FPGA part, basically which can be programmed. Just we have seen FPGA internal architecture. So there is an FPGA, programmable logics, system gates, RAM, same thing. Okay, inside this. And apart from that, there is a processing system. Means there is a microprocessor also there inside the same FPGA chip. Okay, which is termed as processing system. Both of them handshake together, means we can implement the design in FPGA and we can use that design inside the processing system. Or we can, for such embedded applications or some communication applications, we require some of the things to be implemented, some of the things which can be used as it is by the processing system, high-end processing system, and some we can implement inside the FPGA. Both of them will join together using this AMBA interconnect. Okay, advanced. This is a very advanced bus. Okay, AMBA bus, which is termed as very fast bus, which can be utilized for transferring the data from FPGA to processing system. Okay, so in short, what I am trying to convey that latest FPGAs is having a processor and FPGA fabric also, and we can configure FPGA fabric as well as processing system. We can connect them together in order to design any application. So these are the things that are happening nowadays. Okay. For programming FPGA, we are using the Verilog or VHDL we can use. And if we want to program this processor part, we can we can design program in C, Python, or any other language, okay, which can be going to run on latest ARM Cortex CPU. So this is the part of uh, we can say Zinc FPG. Okay, in short, right? So choose any FPGA, whatever you want, but you need to know what are the things available on it. Now let us focus on FPGA design flow. Okay, FPGA design flow. So what actually we are doing till now, we are we have been given a problem of statement. We are given a problem of statement, and we'll try to implement or try to give the description, VHDL descriptions of it. Okay, using Vivado software. So just like suppose we have given a design, we have given a problem statement, design and implement a 32-bit arithmetic and logic unit for ARM-based controller with a power budget of 100 milliwatt. Let's say. So this is the type of problem statement that you have been given. Now you are going, you have to implement a 32-bit arithmetic and logic unit with a power budget of 100 milliwatt. Means we have to design a ALU of 32-bit in such a manner that it can consume only 100 milliwatt of power. How can we do that? How can we check that power? Okay, whether how much it is consuming. That is the topic of next topic of discussion, an important one from the point of view of analysis. Okay, so what we will do, we'll write the code as per our knowledge. We'll do functional simulation verification as we are doing till now. After that, what we will do, which still we have not covered, we'll synthesize our design. After synthesis, what would happen? Whatever the code that we will write, that code would be converted into a gate netlist. Okay, and we have got the information that our design, what we have created, is taking what are the different resources or utilizing what different resources of FPG. Means how many CLBs are going to be used, how many input and output pins are going to be used, how many flip-flops are going to be used, how many multiplexers are going to be used. All that information we can get after synthesis only from gate netlist. Okay. After synthesis, we can implement our design from the point of view of placement, routing. Okay, we can implement our design, and finally, once we have successfully uh, satisfied that okay, our design are synthesizable and implementable, we can dump that program into a FPGA hardware device. Okay, FPGA hardware device. So this is the design flow actually generally being followed. So I have shown you this design flow in a very simple and lucid manner so that you can have a picture in your mind what other steps that we have not discussed till now are being used. But we'll discuss it later on. Okay. Now next part that is important. Once we have tested our design, we have checked our design, we are satisfied, and all these things we have done, we have to check the power. How much power is this our design is going to be consuming. So for that, we need to go for the power analysis flow. design, synthesis, implementation. After the implementation, there is a inside the implementation, we can say only there is an option to analyze the power. There is a power analysis tool, Vivado power analysis tool. Using this Vivado power analysis tool, we can basically check the power consumption of our design. How much power get consumed of our design. Okay. Before that, before actually getting the report, what we can do at the implementation stage or at the synthesis stage, we can apply some user constraint. Means user constraint means suppose if our design is using a clock, so we can specify, okay, how much frequency, clock frequency should be there, because power is directly depending upon the clock frequency, right? So if frequency is going to change, your power is going to be changed. So we need to actually, this power and frequency are relatable. Okay, if one is changing, then another is affecting. So and it may disturb the power budget. In that particular case, we need to first fix the frequency and then check the power and then analyze the power. Okay, so these are the things. Apart from that, if we want if we want to reduce the power or further, if it is more than or above the budget which has been specified in the design. Suppose we have been given a 100 milliwatt budget, but what our ALU is doing, it is taking 120 milliwatt. So in that case, we need to restructure our design or reduce the power of our design and understand what are the power reduction requirements, what are the power reduction techniques that can be applied at the RTL level, or you can say VHDL level. Basically, RTL means register transfer language. So VHDL and Verilog are RTL languages, basically register transfer language. So at this level, what are the different techniques that can be applied in order to reduce that power so that our design can meet the power budget? Okay. So at synthesis step, there are some of the options. At programming level, at algorithmic level, there are some of the options. There are different actually abstraction layers. Okay, we'll discuss this later on. But if we want to analyze, we can analyze. For that, this type of information is there, has been shown to you inside the Vivado software, where you can see you have been shown the type of FPGA you are using. Okay, what is the speed, what is the speed grade of the design? Okay, then this is the important thing. How much power is going to being utilized? Total power is this. Okay, that is 1.812, and this total power is actually is a factor of different power. We'll see that also inside the FPGA. So in this way, we can analyze the power also of our design, right? So there are two main stages of the design flow. You can see first is called the synthesis and another is called the implementation. These are the two new steps basically introduced, or I have told you, because till this step we have been done lots of work. But synthesis and implementation, these are the two new steps. Last is the configuration. So these steps, synthesis and implementation, basically, if you say synthesis, inside the synthesis, what I have told you that it will generate a net list of your design, and this is a technology independent process. Means when it is doing RTL synthesis, it is not referring or keeping in mind any FPGA. It is simply changing your design to the netlist. But when we are doing implementation part, it is a technology dependent part. Then it is following mapping, placement, and routing and configuration. Okay, so this is a technology dependent. It is done by keeping in mind the FPG. Okay, what is the meaning of logic synthesis? Let's show graphically. Suppose you have created this design. So this design is converted into this circuit netlist. You can see over here, whatever the code you have written, accordingly some gates are created, some maybe some flip-flops are created inside the design. Okay. After that, logic synthesis. This is circuit netlist. After that logic synthesis, your design, the same design is going to mapped. Where it is going to map? Inside the to a specific LUT. Means suppose this part is going to LUT 0, this part is going to LUT 1 inside the logic cell. Okay, inside the slice, or you can say inside the CLB. So all of these part are going to map to different LUTs and flip-flops. This is what we called as mapping. After that, once our design has been mapped, then it is placed. Okay, this LUT, this part is placed in this CLB, this LUT, this part is placed in this CLB, and so and so and so and so like that. Different CLBs, because these LUTs may be available in different CLBs, not all CLBs. So every part is can be mapped or placed, you can say, inside different CLBs. Finally, once the CLBs are identified, the last step is the routing. That which particular CLB is connected to which CLB in order to uh, complete this design. Okay, or you can say as per this design, which CLB is going to connect to which CLB or which input output pin. That is done in the routing part. Okay, so you can have, I think you have understood. This is a very important thing. Synthesis, after that mapping, then placing, and then routing. And once it is done, finally the design has been, we can generate a bit file with all this configuration and then dump onto the FPG inside the FPG. Now you can test this FPG device at hardware level, okay, and test it. So hope I would be clear till this point to everybody. This is basically we have actually discussed a FPGA design flow. Okay, we have discussed a FPGA design flow, complete FPGA design flow today. We have discussed about the FPGA introduction and FPGA design flow, complete design flow. Right? Okay. Now, tomorrow I will be taking you to some of the important and very much important aspects of power consumption inside the FPGA, and we will be discussing some of the uh, power dissipation, power reduction techniques also by checking what are the different power contributing factors and how can we basically reduce the power. Okay, okay, what are the different techniques that we need to follow or available at the inside the literature that we will check. Okay, so till now, until then, keep practicing, and if you find any doubt, please let me know. Okay, so I'm stop sharing my screen. If you have any doubt, please let me know.